まずはじめに、汎用基盤技術研究グループのグループディレクターも兼務されておられる、杉山正史より、グループの紹介を行います。杉山グループディレクター、どうぞよろしくお願いいたします。
今度は汎用グループのディレクターとして、汎用グループの研究成果を簡単にご紹介したいと思います。まずこの汎用基盤技術研究グループですが、機械学習の理論構築やアルゴリズム開発を行うということをメインにしております。で、実際には大まかに3層構造になっていまして、基礎の数理から学習や最適化の理論構築、そして、学習、推論、探索、検定などのアルゴリズム開発を行うということになっていまして、これを実世界の応用につなげていこうというふうに考えています。で、現在、13チームで活動をしております。で、いくつか研究成果をご紹介できればと思いますが、近年、基盤モデルという言葉があちこちで使われるようになりましたが、これまで機械学習の古典的なパラダイムとしましては、適切な大きさのモデルを準備して、それをゼロから訓練データを用いて学習するということをしてきました。それに対して近年、汎用的な巨大モデルを準備して、それを大量のデータで事前学習するというパラダイムがやってきました。で、さらに最近は、その事前学習の後に事後学習を行って、そしてテスト自推論を行うといったこんな流れになっています。で、この事後学習というのは、モデル全体であったり、モデルの一部を下流タスクの追加データで微調整するということになっています。で、研究のキーワードとしましては、AI アイアライメントとか最近言われてるんですが、アライメントとか、スーパーバイズ、アンスーパーバイズ、ファインテューニングとか、プリファレンスオプティマイゼーション、レイフォースラーニングフロムヒューマンフィードバックとか、AI フィードバック、こういったテーマで研究されています。また、テスト自推論としましては、主にトランスフォーマーを考えまして、モデルは大きいのでもう固定しておいて、モデルは変えずに、プロンプトに追加データを与えて、うまく処理する。あるいはそれを自己学習していくということをしています。研究のキーワードとしましては、モンテカーロサーチとか、インコンテクストラーニングとか、チェインオブソートとか、トリーオブソート、こういったものが、研究されています。で、こういった枠組みの下で我々の研究いくつか見てみますと、まずは、事前学習の段階と事後学習の段階で、環境が変化するということがよくございます。で、そういった場面で、オンライン学習でうまく時間変化する環境に適応していこうという研究を行っています。で、今日はあんまり細かいことは、説明できないですが、これまでは多数のモデルを用意して、アンサンブルを取ることによって、この動的リグレットを最適化できるということが示されていたんですが、それを一つのモデルで達成するということに成功しました。あるいは、多数のモデルをやっぱり使うんですが、従来は、訓練データ、最初に事前学習から訓練データを取っておく必要があったんですが、それなしで、テスト時に、このラベルなしデータだけを使って、適用するというテストタイムアダプテーションという方法を作ることにも成功しました。また、分布が変化するような状況で、テンソル分解というのをうまく使うと、組み合わせシフトに適用できるという、こういった成果も得ました。で、これは低ランクを仮定することによって、一部だけ観測されていれば、他の部分も穴埋めすることができるということで、分布がシフトしてしまって、分布外適用したいときとかに、低ランク構造がうまく活かせると、一部の観測が得られていれば、観測を得られてない部分に関しても、ちゃんと値を予測できるということで、興味深い成果を得ました。で、2番目、文脈内学習。これインコンテキストラーニングの日本語訳なんですが、これが、現在非常に注目されています。例えばチャット GPT で、11は2で、23は5で、83は21でといったこういうものをプロンプトに与えて、で、5、27は何ですかと聞くと、ちゃんとこの与えた例から何かを学習して、このハテナを予測してくれるということで、で、実際にやると、2つの数字の和が、与えられているということなので、5と27は32が答えですというのがチャット GPT で出てきます。で、これもちろん、この5つのデータを、トレーニングデータとして与えれば、解けるのかもしれませんが、それを、モデルを変えずに、プロンプトにこれを与えることによって、こういった能力を学習させようということが行われています。で、この研究に関しまして、基礎的な理論研究を行っておりまして、例えば、この文脈で使われているトランスフォーマーの予測が、ある意味でのこのミニマックス最適性を持っているということを数学的に証明したり、その中で使われている2層のニューラルネットワークの特徴学習が、待機的な最適性を達成しているということであったり、事前学習による学習精度を、どうやって改善していくかという議論であったり、さらにこの、チェーンオブソート、チェーンオブトリーですね。思考、トリーオブソートですね。思考の木構造 を自動的に生成するにはどうすればいいかといったこんな話題で研究成果が得られております。あともう少しオンラインの場面で蓄次的な意思決定というのが非常に重要な課題になっています。これは環境からのフィードバックを通してモデルを蓄次的に更新していくというもので、先ほどの、基盤モデルの議論とはもしかしたらちょっと違うかもしれませんが、例えば、そこそこ小さなモデルがあったとすると、それを環境からのフィードバックを得ながら、蓄次的に更新していくというような場面を考えています。でそれに対しても様々な成果が得られていまして、組み合わせ最適化とオンライン学習を融合することで、いろいろ新しい成果が得られています。例えば、離散突解析という技術を使うことによって、こういう離散の突構造を持ったものに対して、最適なアルゴリズムを作ることができるようになったり、コードが今までは離散的だったものを実数値に拡張することができたりしています。また、この文脈で、やっぱりリグレットの解析が非常に重要になってくるんですが、そのミニマックスリグレットをより精緻に理論解析するという研究を行ったり、さらには、これ非常に面白いんですが、環境適応的に学習するということで、確率的な環境ですと、データが統計的に独立な状況で得られるような場面に対して、敵対的な環境ですと、一番嫌なデータをアドバーサリーが与えてくるといったような状況になっていまして、この二つがある意味相反するものなんですが、この相反する2つの環境、両方において同時に最適性を達成できるという画期的なアルゴリズムも作っております。最適化の文脈では、2段階、多段階最適化というのがいっぱいありますが、そのうちの2段階の部分というのが、特に機械学習で有用でして、上位の問題では普通にパラメータに対して訓練誤差を最小化しようとしていて、下位の部分では、ハイパーパラメータに対する検証誤差を最小化するということをやっていまして、通常機械学習の文脈では、この下位の問題はあんまりちゃんと解かずに、上位の問題ばかり一生懸命解いてるんですが、これをちゃんと解くことによって、より良い性能が期待できるということがあります。ただ従来の研究では、下位レベルの問題に制約条件がないとか、目的関数 G が微分可能で共突であるといったテクニカルな条件が必要でしたが、今回これらを外すことに成功しました。リーマン多様体の制約をつけても、ちゃんと段階最適化が最適に解けるということで、設定値の推移であったりとか、スティーフェル多様体、直行行列の空間であったりとか、二重確率行列の空間、こういったところで、二段階最適化がきちんと行えるというアルゴリズムを作りました。また、微分不可能な場合、G が微分不可能な場合に対して、ラストのようなスパースな問題に対して、最適性の保証がついた解法を初めて作ることに成功しました。であと、最後、因果推論の話なんですが、これ一つ応用例なんですが、因果推論のアルゴリズムを、博士課程の進学者数の、因果メカニズムの解析に使おうということで、これ、文科省のナイステップと一緒に共同研究させていただいたものなんですが、いろいろ観測されるデータを集めていただきまして、これらを使って、リンガムという、清水先生が作られている方法を使って解析するということをしました。ちょっと今日は残念ながら詳細には踏み込めないんですが、こういった因果グラフをデータから作ることができて、DC1 の採択者から博士課程の進学者数が因果関係を持っているというのは自然な結果ですので、これがちゃんと観測されたりとか、博士課程の進学者数と、1年後の DC1 の採択者数が因果関係が非常に強いということが分かったり、で、逆に、博士課程の修了後のポスドク就職者数と1年後の DC1 の採択者数には因果関係が見つからなかったということで、いろいろ面白い結果が得られていまして、これは今後さらにデータを集めたり、いろいろ方法も洗練させていくことによって、より意味のある結果を得て、最終的にはポリシーメイキングの方に貢献できるような結果が得られればなと思っております。で、その他、各チームいろいろ、また細かい成果もたくさん出ていますので、ウェブページで、全チームのポスターを、公開しておりますので、ぜひこれらをご覧いただければと思います。では、成果の説明に関してはここまでで終了にしまして、後半はパネルディスカッションをしたいと思っています。はい。
はい。で、パネルディスカッションに移りますけれども、各グループのパネルディスカッションでは、Zoom でご参加の方々は、画面下部の Q&A 機能によりご質問いただくことができます。また、この杉山グループディレクターのこのプログラムのみ、英語でディスカッションを行われます。Zoom の字幕機能にて簡易な翻訳を利用することができます。パネルディスカッションのテーマは、Time Aware Machine Learning, State of the Art and Future Perspective です。で、先生、じゃあよろしくお願いします。
Okay, thank you very much. So, actually, the term time-aware machine learning is not really a generic term. This is very specific for this symposium. But I think nowadays it's quite important to consider the time axis in the machine learning in the community. And we have 3 team leaders today, and they are all working on like machine learning related to time, like continual learning and dynamical systems and online learning. Okay, so in the beginning, as introduction, so I asked them to present their research briefly. We have a bit of question and answer.
Hello, everybody. So my name is Mohammed Imtiaz Khan. You can call me MT because it's easier to remember. And I lead the team on approximate Bayesian inference. The goal of our research is to build a low-cost AI system that can learn like humans, like animals, how we learn. So what we actually usually do is that when we observe some new data, we somehow squeeze it in our brain, that information, and we continue to do so throughout our life. We want to design AI systems that are capable of doing similar kind of information processing. And we believe that that leads to a very low-cost system because it doesn't need to be updated all the time. Rather, it can learn as the new data arrives. But this is very, very different from how deep learning paradigm right now works. It's very, very costly. It's because you have to collect all the data that you want the system to know at the same time. So in the image here, I show that there's a huge world out there. It's like the whole internet, and it contains all the data. And now there's a lot of work being put in collecting this data and then designing some model that will be able to squeeze in all the knowledge at the same time. So currently, how deep learning is done in this, brute force data collection and model design, it is unsustainable. It requires a huge infrastructure, which allows some people to control the whole system. It favors monopoly, not able to bring democracy back into the system. So we think that it's really harmful, and we need to change this. And we've been working on Bayesian principles to fix these things. Bayesian principles have been known for decades to be foundational in many systems, like in economics and social science. Even brain has been shown to follow some of the Bayesian principles. But right now in deep learning, the Bayesian principle doesn't fit really well. And we've been trying to fix this in our research. So here's some of the works that we have done in last 10 years or so. The biggest work that we did was to show that many algorithms in machine learning, in deep learning, they can be seen as optimizing some kind of Bayesian objective. So we always have some Bayesian flavor in these algorithms. And now we are using this common framework that we developed to understand the sensitivity of these algorithms. For example, if the data is added sequentially over time, how sensitive these algorithms are to those perturbations, and how can we adapt these algorithms to include the data in the sequential fashion. So we use this idea basically to design new algorithms that can learn continually, like how humans learn over time. They can also make use of data that's split across different locations. So something that is called federated learning. So suppose lots of people, they train their own model and they upload it on some place like Hugging Face, then we should be able to reuse their knowledge and improve our model over time. We've also worked a lot on large language models, where you can use some kind of merging of models to improve the language performance of the models. So that's all.
So great, thank you very much. So let me ask a few basic questions. So your team is approximate Bayesian learning team. And nowadays deep learning is like a huge scale system, and many people think Bayesian is not scalable. You are fighting with it, right? Yeah. So can you briefly explain how did you overcome this difficulty?
Yes. So this is really, I think this is a success story for good mathematical foundation. It takes hard work to build it, but it pays off in the end. So the reference one of this Bayesian learning rule that we worked on, actually the first paper that I wrote as soon as I joined AIP was about this idea. It took many years for us to convince the community to show that if you have actually a proper foundation which unifies lots of algorithms, then it's easier to borrow strength of different types of algorithms and make them practically feasible. So just last year, we had the paper, the reference number 3 here, where we are able to use Bayesian learning at the GPT-2 level, and we're able to learn at that scale without any problem, something that nobody else has been able to do before.
So can I simply regard as that something people can do with standard deep learning can be transferred to Bayesian work nowadays?
Yes, so it's possible. Of course, more work is needed, but it's definitely possible. So you can download our code like this now, and you can run it right away.
Oh yeah, and then of course you can compute uncertainty. That's the practical advantage.
Yeah.
Other than uncertainty, can you think of any advantage of Bayesian approach here?
Yes, so exactly the rest of the points that I've written here. There's a relationship between uncertainty and sensitivity, meaning that if new information is arriving over time, somehow your model is going to change. It's sensitive to it. And if the information is not new, then the model doesn't change much. And we have shown that this kind of how much the model is going to change, you can calculate that estimate by using the uncertainty estimate that comes from the Bayesian idea. So now you have some sense of, should I retrain my model from scratch, or should I just update it a little bit? How long should I wait before updating my model? These questions can be answered by using the uncertainty.
Oh, that's great. I still have a lot of questions, but maybe I have to stop. Then Kawahara-san, to continue.
Good afternoon. I'm Yoshino Kawahara, the team leader of structural learning team. So in structural learning team, we are developing the machine learning algorithm that incorporates some prior knowledge to your learning process, which is given by the form of some structures in data or mathematical models related to the problem to make the algorithms more interpretable or to modify the efficiency or the performance of that. Especially recently, we focus on these topics for learning with data that's generated from a dynamic data generation mechanisms, where prior knowledge would be like some sort of known physical property of the underlying dynamic processes. So we are especially interested in the information for this problem using the so-called Kupma operators or its adjoint operator called transfer operators, which give general representation of dynamic systems, and they have high compatibility with many machine learning methods such as kernels and neural networks. And we have approached to this problem from various aspects, from theory to application to several machine learning tasks, and application to the design neural network architectures. And for example, as for the estimation perspective, operators in general defined in infinite measure space. So there is a fundamental difficulties to estimate using finite data because we can just use finite samples in practice. We have tackled these difficulties using several mathematical tools, such as the one discussed in the episode. And also we applied this kind of principles to several machine learning tasks, such as time series forecasting or reinforcement learning, and also apply to design of neural networks architecture. For example, recently we gave generalization of the state space model, which is a fundamental time series model known for some time, using transfer operators that is defined in the space, even by kind of the embeddings of probability distribution that define this knowledge. Also, yeah. Also, we the big okay, and also because and also we use this principle to design a new neural network architectures, because many machine learning problem models can be regarded as dynamic systems of signals. So in the future, we'd like to pursue these directions. Yeah, in a wider.
Okay, great. Thank you very much. So I'm personally a big fan of this direction, because it's not really a kind of explored topic in the machine learning community quite actively. And I think there are a lot of potentials here. In particular, you found some connection to this dynamical system research and current state-of-the-art machine learning technique. So I'm sure some basic research is really ongoing, and you have a lot of interesting results. But from a practical viewpoint, so do you have some particular algorithms that can be almost immediately applied to some problems?
Okay. Yeah. Yeah. Recently, we are exploring those applications, and yes, for example, so time series forecasting and reinforcement learning. We successfully developed machine learning algorithms for these problems that can achieve better performance.
So in that case, I think you need some knowledge from the physical system behind the thing. How do you incorporate that kind of knowledge in the algorithm?
Okay, so we do not necessarily need prior knowledge. I mean, we can just use some physical property that should be, that should exist in program. For example, stability for forecasting or.
I see. So it's more like a constraint. As long as you have a constraint, then the rest is more like data driven. So like already some software exists for that, for some like simple problems.
We just approach it code for papers. So we don't have
And also, like, do you try to guarantee the kind of prediction performance in some way?
Yes. This kind of framework, also can be used to develop such theory. Because
it's quite challenging.
It's of course it's very difficult from mathematical point, but it's closely related to the many mathematical concepts discussed in So
Okay, great. Thank you very much. So then finally, Hatano-san, could you introduce you briefly?
Okay. My name is Kohei Hatano. I'm a team leader of computational line theory team. Our team mission is to investigate machine learning problems from theoretical computer science perspectives. Let me show you some examples. Also, our primary goal is to develop a theory of online decision-making framework. Our recent results include many applications of online learning theory. As you see in this figure, online decision-making framework is quite simple. We have decision maker or player, and another one is the environment. They interact with each other, and player gets feedback, and the final goal is to get some performance guarantee on the player's strategy. Here, there are some interesting applications. So Satoe Hiro in our team interactively working with computer vision researchers, and he obtained many interesting application results, such as aggregation of online tracking in the video. It's quite hard in general, but he solved the problem by combining many trackers at the same time using the classical online learning techniques. It's quite simple, but the result is remarkable. And interestingly, he also devised offline learning techniques for noisy level by formulating it as an online decision-making problem. This is an interesting result too. Here, the point is that online decision-making techniques is useful, of course, useful in online environment, but also it can be useful in other scenarios, such as offline optimization. Another example is 5G or 6G wireless communication, mainly led by postdoctoral researcher Dr. Hashima. Here, many applications result in online optimization problems in the wireless communication scenarios. Mainly, he formulated the problem as a bandit game and had a lot of applications such as channel selections over many different characters of channels, like communication, 5G, or the Wi-Fi and so forth. And also recently, he working heavily on using new machines such as unmanned air vehicle or other new instruments. Another direction of our work is offline optimization, but it's inspired by some insights from combinatorial online optimization. More precisely, our optimization is based on a kind of succinct data structure, such as data decision diagram. Well, in general, machine learning or operation research, they deal with a huge scale of optimization problem. And as is often the case, it contains a huge set of linear constants. And our recent finding is that if such huge set of linear inequality with discrete coefficient have discrete coefficient only, then it can be compressed somehow by representing successively with a decision diagram. And if the resulting decision diagram is small, we get concise but equivalent inequalities. So by using our method as a pre-processing, then we can solve large-scale machine optimization problem with linear constraint with faster and smaller memory consumption than using vanilla optimization solver. Yeah, that's a recent summary of work. Thank you.
Okay, thank you very much. So in the first page, you talked about online learning.
Yes.
And classically in online learning, we use a simple model. But otherwise, updating the model is quite time consuming and costly. So in your research, so what's the typical size of the model?
Right. Well,
or structure?
So far, we are not dealing with large models such as LLMs and so forth. Let's say relatively small, but in our case, we are thinking of, let's say, really online scenario, such as online optimization in wireless communication, where each machine is relatively small instrument. So maybe the memory and energy consumption are limited.
So it is a distributed system.
It could be distributed, and each machine doesn't have large computational power.
And do you update the entire model in each time step or only part of that?
Well, in our case, we are relatively simple bandit or online algorithm, so it's update entire model. But we could extend to use such relatively large models. So,
I think distributed systems are quite important in that kind of scenario. And have you ever done any research along that line?
well,
The distributed optimization. There's also a big community there.
yes. And as for theory learning, there's a lot of mystery. So I haven't solved with theory results, but as for applications, we tried several applications with multiple player scenario.
Okay, thank you very much. Actually, I asked already a lot of questions and we only have 10 minutes to go. And so if audiences have questions, please write your questions in the QA box. And until then, so I want to have a bit more discussion about this time-aware machine learning. Because I'm interested in this topic because I'm basically a distribution system partner. I believe world is changing and our machine learning system should cope with this changing environment. Then, so all of you are working on continual learning and dynamic class system, online learning. These are like similar, I think similar approaches, but mathematically quite different. But what's the kind of ultimate challenge in your line of research? Maybe in the short term, a bit longer term, can you say a few words on that?
Yeah, for me personally, trying to represent what you know well enough so that you're able to handle some changes that are very new. This is a fundamental question.
So does it include like change detection also? You should be aware that something has been changed.
Of course, yes. I mean, in the sense, defining what is new and what is old is a very foundational question. So you would say that sudden changes happen when something looks unfamiliar. It's completely new. So, and you can make sense of it by basically trying to predict it and looking at your mistakes, how many mistakes you're making. And then you have to cope up with it. So you have to think about, have I seen this before? Do I know about this? Is it in my system? And this is easier to do if you have a simpler model. But if you have a really large model that has its knowledge derived from a huge data set, it's difficult to figure out where the source of uncertainty comes from.
And usually Bayesian is the most suitable.
I think Bayesian approach tells you the gold standard to what to look for, and so it gives you some upper limit on what could be ideally possible. And of course, you have to, when you design a system that doesn't have the capacity to model everything, you have to make certain bets. So you need to think about what kind of uncertainty I think that will arrive in the near future and safeguard them. So that's where you will put the resources. So uncertainty kind of helps you to decide what to store, for example, how to represent the knowledge. So yeah.
Great, thank you very much.
There's a question. Question is, what are the key distinction between the time-aware and adaptive machine learning approaches?
So I must say time-aware is not really a defined term. So adaptive machine learning is one of them. But we have a lot of different terms like continual learning, dynamic classification, online learning, distribution system, all are related topics. And I just want to cover everything without using the current known term. So that's time-aware machine learning. I don't know whether this is not really a definition, but yes, the concept is something like that. Then Kahara-san, how about you?
Okay, so I think the operator theoretical approach to the system is quite general.
Now it's a hot topic.
Hot topic, and also, but so far, I think it's the beginning of so the combination of such a framework to machine learning is just a beginning, and I think can be useful in various applications.
So what's the technical challenge there? The continuous time? Or...
One important thing is that operator is defined in infinite operation, and we can use just the finite sample. So it is fundamentally difficult to extract information of operator.
I see. That sounds very interesting. Then Hatano-san, how about you?
Okay. Well, up to now, online learning theory has been studied within a very theoretical communication only. But recently, such as wireless communications, there seems real online application coming. So I'd like to investigate and communicate with such people and find a new program which motivates a new theory of online learning. So by looking at concrete problems in the applications, maybe current theory lacks something. Then we could develop new theory which will resolve it. That's my short term and middle term goal.
Oh, that's good. So let me also talk about like my personal interest, because world is changing and I'm interested in distribution shift. So we want to have a method that can overcome changing distribution. But the problem is all the research previously was, so they needed some kind of assumption for the changing distribution. If our presumption is correct, then okay, the method works very well and it enjoys some theoretical performance guarantee. But in reality, we don't know that. So it's more like a gamble. Okay, let's believe assumption A is correct and use this method. But in reality, it doesn't work because assumption A is not. There's no way we can assess whether this assumption is correct or not. So my personal goal is to have a kind of machine learning method that does not require, I don't say any assumption, but that require much weaker assumption than previous method. So maybe the performance is not so good because assumption is weak, but still we can guarantee that minimum performance doesn't go well. So it doesn't go wrong and it has the minimum guarantee. So then that should be the method we can use in practice in the beginning. But in the beginning, we don't really have any knowledge about the problem, and we only have small amount of data, but we can apply that method as a reliable methodology. So then we obtain some reasonable solution. Then based on that, okay, we need to make a decision whether we invest more on this topic and have more data, more knowledge, and use more sophisticated machine learning techniques. Nowadays, I think only this second step was investigated. So we focus on a particular setting and we try to achieve a champion performance. But that's the second step and only possible in some specific application areas. But in many unexplored areas, still we are not sure whether machine learning is really useful. Then we need a kind of very generic method that is not strong enough, but still we have some guarantee. So that's the kind of direction I'm quite interested in. So I try to connect like my personal feeling and your current direction. Then I think like performance guarantee and computation are kind of two issues that we need to explore this time-aware machine learning direction. Then so time is limited. Can you just quickly say your challenge?
My challenge in general or
anything?
Yeah, I think I mean one is definitely a technical challenge on how to, like, you have limited resources and you need to prioritize it based on which would be the biggest threat to your system. And I think we need to find some general mechanism which allows us to make this decision easily for a wide variety of scenarios.
The easily means non-export.
No, easily means the rule remains the same. To make a decision on how to allocate, like based on entropy or something like that, or uncertainty. So that's the technical challenge. I think the second challenge that I think is a non-technical challenge on how to convince the community that they need to move from this big model, big data setups to a more time-aware, dynamic information, because that is something that is absolutely necessary for it.
That's something I wanted to hear. That's great. Thank you very much. Then how about you?
I'm interested in so the concept I don't do, the concept discussed in master. Maybe so if we combine those, maybe for example, your purpose also could be achieved partially. So, yeah, I'd like to pursue that achieve.
There must be many different approaches to weaken the function. So like, we are kind of competing, but I think the goal is quite the same.
Not competing.
In terms of approaches, we are competing, but the goal is the same.
Yeah.
So ideally, we want to combine all at the same time.
Yeah.
Thank you. Then Hatano-san.
As for time consumption, in many cases, discrete optimization is relatively harder in many cases. Online discrete optimization, especially for nonlinear objectives, is a very challenging direction. Where in the offline case, there are many efficient discrete optimization algorithms for nonlinear case. But if you consider online variant, they are still unknown. That kind of direction can be mathematically and also practically.
So along that direction, still there's no good method
No.
to solve the problem. That's really an open direction to go. Okay, so we have to finish now. So sorry that my time management was not so good. So we wanted to have half an hour more to have more discussion. But if the audience has more questions, please send us an email. Hope that we can have more discussion offline. Thank you very much.